Hello, this is Rick from MathX, and today we'll be doing number 23 from the AMC 10B of 2020. Now, this problem is another problem in the final 20 of the AMC 10 test that is surprisingly easy. It's a number 23 on an AMC 10B test, so you expect it to be really hard, but once you actually stop and take time to solve this problem, you realize it's quite easy, and it just requires a couple counting tricks and some easy intuition. Way easier than its ranking on the test. Anyways, without further ado, let's go through the problem so I can exactly show you what I'm talking about. Square ABCD in the coordinate plane has vertices at points A, 1, 1, B, negative 1, 1, C, negative 1, negative 1, and D, 1, negative 1. Consider the four following transformations. L, a rotation of 90 degrees counterclockwise around the origin. R, a rotation of 90 degrees clockwise around the origin. H, a reflection across the x-axis, and V, a reflection across the y-axis. Each of these transformations maps the squares onto itself, but the positions of the label's vertices will change. For example, applying R and then V would send vertex A at 1, 1 to negative 1, negative 1, and it would send vertex B at negative 1, 1 to itself. How many sequences of 20 transformations chosen from L, R, H, V will send all labeled vertices back to their original positions? For example, R, R, V, H is one sequence of these four transformations. I'll send the vertices back to their original position. So this problem is a weird mix of counting and geometry, because it's asking us to count the number of way of 20 transformation sequences, but it wants us to do so on a coordinate plane geometric figure. So since there's even a little bit of geometry in this problem, we should draw a diagram to understand what we're really dealing with here. So we should quickly take time to do that. So here we have it. Square ABCD, and we see that A is located around where 1, 1 would be. B is located where negative 1, 1 would be. C is located where negative 1, negative 1 would be. And D is located where 1, negative 1 would be. So we've got an idea where A, B, C, and D would be. Now that we have an idea where each of these vertices are located on this square, let's try to get an idea how each of these transformations would affect the square itself. So let's take a look at the first transformation. L, a rotation 90 degrees counterclockwise around the origin. So counterclockwise means it goes against the clock's direction. And since the clocks would go like this direction, counterclockwise means A would go to the left. So that means A would move 90 degrees to the left, to where B once was. With the same idea, we see that if we apply the same kind of idea to rotation R, we can understand that when transformation R is applied to A, it'll move 90 degrees clockwise, so this direction, down, to where D once was. If we do the same kind of thing, except no longer with rotations, but with reflections, we understand that when transformation H is applied to the square, A will be mapped to where D is, because it'll be flipped over the x-axis. The x-axis is the one that goes horizontally. And then if we apply transformation V to the square, A will go to where B was, because it'll be flipped over the y-axis, the vertical axis. So then we kind of have an understanding of what each of these transformations does. V and L will move A to where B is, and transformations R and H will move A to where D is. So we see that these transformations either move it to the left or it moves it to the right with equal probability. So this is what each of the transformations does to it. But we're not supposed to be dealing with just one transformation. We have to find out how many sequences of 20 transformations chosen from L, R, H, V will map A back to A, B back to B, C back to C, and D back to D. So we found out what each of the transformation does to A. So now let's try to figure out how many sequences of 20 transformations are there. Well, the first transformation could be any of these four options. And the second transformation could be just as well any of these four options. And this remains true for each of the 20 different transformations. There could be four different options. So the total number of sequences of 20 transformations is just 4 times 4 times 4, 20 times. And 4 times 4 times 4, 20 times can be more simply written as 4 to the 20th. However, we have 4 to the 20th as the total number of 20 transformations. But in our answer choices, we see that everything's either 2s or 3s. So it'd probably be in our best interest to convert 4 to the 20th in terms of 2. Now 4 is just 2 squared. So this is just really 2 squared to the power 20th. And using simple exponent laws, we can do 2 times 20 to get that 4 to the 20 is equal to 2 to the 40. So this is the total number of 20 transformations. So now we know the number of 20 sequence transformations, and we know what each transformation does to the shape. So let's try to understand how could we make it so that the sequence of 20 transformations using the four transformations provided will map A back to A, B back to B, and C back to C, and D back to D. So looking at the transformations, we've already noted down that left will move A to B, and V will move A to B, while R will move A to D, and H will move A to D. Well, it might be easier to keep track of these, not in terms of A's, B's, C, and D's, but in terms of numbers. Currently, A lies in the first quadrant. B lies in the second quadrant. C lies in the third quadrant. And D lies in the fourth quadrant. Because all the options either move A to B or A to D, it becomes quite clear that after the first transformation, A will move to an even number quadrant. And since both of these even number quadrants are adjacent to odd number quadrants, and these transformations will just move them to their adjacent squares, once it's at an even quadrant, the next transformation will move it to an odd quadrant. So this lets us set up a relationship between the number of transformation and the number quadrant it will be in. We see that for any odd number transformation, it'll move it to an even number quadrant. Similarly, any even number transformation will move it to an odd number quadrant. Since we're dealing with a 20 sequence transformation, 20 is an even number, so it'll be in an odd number quadrant. So A itself will be in either quadrant 1 or 3. Now, if we want A to line up on A, it has to be in quadrant 1. So since after these 20 different transformations, A could be either 1 or 3, two different possibilities, but we only want one possibility out of it, A has a 1/2 chance of being in the right place. However, that's just not our sole answer, because if A is here and B is down here, that's not going to work as well. Well, B always has to be adjacent to A, no matter what. So if A is here, B could either be where B is supposed to be, or it could be where D is right now. So, once again, B has two options it could be in, but it can only be in one right answer. So B has a 1 chance of being in the right place. So, after these 20 transformations, A has a 1/2 chance, and B has a 1/2 chance of being in the right place. So, collectively, that gives us a 1/4 chance of A lining up on A, B lining up on B, C lining up on C, and D lining up on D after these number of 20 sequence transformations. So the number of possibilities that will work will be the probability of it working times the total number of transformations. So in this case, the total number of transformations is 2 to the 40th, and the probability of it working is 1/4. So the total number of ways in which this will work is 2 to the 40th divided by 4. And since 4 is just 2 squared, we can cancel out the upper exponents to give us that the total number of working possibilities is 2 to the 38. So an answer of C. So this problem wasn't that hard. We just had to get a visual on it and then connect the quadrant vertices to the number quadrant it is in. We also had to understand how each of these transformations would affect each of these vertices and the total number of transformations there could possibly be. But this is a number 23. And typically number 23s are much harder than this, typically involving a more advanced concept in counting, like recursion or generating functions. This problem we could solve just by using simple counting methods, showing that if you just try and have confidence on the test, you could solve these harder problems with just these basic concepts.